Hello, today we're going to cover position time graphs and we're going to actually convert them to velocity time graphs. Right now I have two graphs set up. One of them is a completed position time graph and the other one is an empty velocity time graph, which I'm going to transfer all the information from the position time graph to a velocity time graph. All right, before we do that though, let's first figure out what's going on in this position time graph. The easiest way to do this is to divide your graph into simple sections. So you'll notice that here's a line, there's another one. You can actually divide it up into three different sections and then analyze them separately so it's easier for you. So let's do that. Section A, Section B, and Section C. Okay, let's first look at Section A and figure out what's going on. You'll notice that the position is 100 kilometers east after 1 hour. So the times in hours, position is kilometers east. Notice you could put negatives here if you like, or you can label that west, it doesn't matter, okay? But essentially, it's pretty much a straight linear line. And so if you calculate the slope of A, then the slope, remember, is equal to constant velocity. And so the slope in this case is going to be 100 divided by 1 hour. And so this object, or let's say the car, is traveling at 100 kilometers per hour east. Let's figure out what is going on in section B. So after the first hour, it stays at 100 till the second hour. So therefore, it's not moving because its position is still 100 kilometers east at the first hour, and at the second hour, it still remains in the same location at 100 kilometers east. So in this case, the car is either stopped, or you can call it at rest, or the velocity is equal to 0 because the speed is 0, right? And it's going nowhere. In section C, this is the third hour. It's going from 100 kilometers east back to the origin, so back to the start. You'll notice the slope is negative. Therefore, it's just going backwards. It's not going slower, but it's going backwards and it's going in the west direction. So therefore, if you take the slope of this is still going to be 100 in 1 hour. So 100 divided by 1 is still 100 kilometers per hour. In this case, it is west. So constant velocity at 100 kilometers per hour west. You'll notice that the slopes here, A and C, have the same value, okay? Except A, the slope is positive. That means it's going east or forward. And C, the slope is negative. So that means it's going backwards or it's going west. Okay, now that we know what's going on, it pretty much constant velocity until it hits 100 kilometers east, then they stop for an hour and then they head back home for at the same speed at 100 kilometers per hour west. So that's what's going on in this graph. Now we're going to actually draw a velocity time graph. So in other words, you're going to graph the speeds right here against the same times. All right, and if you want to graph the velocity or the speeds, these are the slopes, remember? And we're going to graph them right there. Okay, so our first hour is going at 100 kilometers per hour east. So let's write that in. Let's say this here is 100 and the speed is kilometers per hour east. It's the same speed for the first hour. So therefore, this is going to be the same speed all the way for the first hour. Like so. So in other words, if it's a half an hour, it's still going at 100 kilometers per hour east. Remember, we are plotting speed or velocity in this case. Then it's at rest for the second hour. So from 1 hour to 2 hours, it's going nowhere. So that's section B. And then the last part, which here is going to be a negative 100 kilometers per hour, or you can say 100 kilometers per hour west, it's going to be here between the second and third hour, like so. Okay? And that's pretty much it. So this graph, which is a position time graph, tells you where you are. And this graph here tells you how fast you are going. All right? So this tells you where you are. And this graph tells you how fast. How fast. That's essentially the difference between these two graphs. So why do we do this? Well, you know, in math class, they tell you that eventually some of you might be taking grade 12, that vector calculus course. Well, this is actually calculus right here. Typically, what you do is you graph a position time graph in calculus, and then you take the slopes, or they tell you to take the limit or take the derivative. And when you do that, you're going to get how fast. And that's essentially what calculus is. This is sort of like that pre-calculus to help you get a head start in that grade 12 calculus course. All right, it's time for you guys to practice. There is a worksheet and actually a package, a PDF, and in that package there are 4 pages. So the first page looks like this, the second page looks like that, the third looks like that, and then the fourth looks like that. Okay, so what I'm going to do is I'm going to walk you through the first page. And then after, I'll let you try to do the other 3 pages on your own. All right, so the first question, it says find the velocity for each sections. So you'll notice that I've labeled each sections conveniently for you. Okay, so let's find the velocity of the first one. That means we're going to take slope for each line. So this here, the slope is 0. That means it's going nowhere. It's at rest. The object is at rest. And same with section C. So these two are pretty easy. When you do your work, go ahead and do all your work on the graph paper. When you do this on a quiz, test, or exam, I expect you to do that. Just fill this page with calculations. You don't need an extra piece of paper on the side to do it. All right, let's do the slope of B. And I'm going to put it over here to allow for more room. Remember, the slope is equal to d2 minus d1 over t2 minus t1. Or you can do rise over run, whichever is easiest for you. Okay, so let's figure out which is d1 and which one is d2. Keep in mind that the point on the right is always the second point, and the point on the left is always the first point. So when you read, let's read the second point first. This is going to be 20 and then minus 45. The time here is going to be 2.6 minus 1.4. That works out to be 25 over 1.2, and if you work it out on your calculator, that's going to be minus, because remember it's minus 20, or sorry, 20 minus 45, which is minus 25. If you work it out on your calculator, that's going to be minus 20.83 repeater. Okay, that makes sense. It is a negative slope. Therefore, it is going backwards. In this case, we have our direction north. So that means in section B, it's traveling south. So if you want to write that, you can. So I'm going to write that down. This is going to be 20, let's round up, 20.9 meters per second, and this is headed south. Okay. If you want to write negative north, you can. Let's do D. The slope of D over here, again, rise over run. Remember, the point on the right is always 0.2. The point on the left is always 0.1. So here we go. V is equal to, let's read that, and that looks like it's 65 minus 20, and then we have 5.2 minus, it looks like 3.2. All right. That should give us, I believe, 45 divided by 2, which is 22.5 meters per second. In this case, it is headed north because it is a positive slope, and positive is north. Okay, let's skip number 2 for now, all right, and let's go right to number 3. Number 3, it says draw the velocity time graph, and we're going to use the graph below. All right, so let's look at our scale right now. We have a maximum value of 22.5, and we have the lowest number of negative 20.9-ish. Okay, and so we should figure out the range. Remember this in math, the range, so that we're able to plot this, okay, and pick the correct scale. Because I think the hardest part in math sometimes is, or hardest part in graphing, is picking the correct scale. Now you'll notice I'm filling out the time. You'll notice time does not change. So the time section is identical, which makes it really easy. All right, so to pick the scale, I'm going to say our maximum range here is from 22.5, and our minimum range, or the minimum lowest value, is negative 20.9. Okay, if you add up all the numbers in between, okay, so let's round this up. We're going to round this up to, let's say, 25, and let's round this up to 20. Approximately, there is 45 units, or let's say 25, just to be on the safe side. So there's 50 units. Okay, so 50 approximately is about 50 units. Okay, so there are 50 units that we need to graph. Okay, the highest number is about 25, and the lowest number is not quite 25. So we have to make sure we add all of it in here. So 50 units. Let's figure out how many divisions we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 50 units divided by 10 divisions. That means each major division here is going to be worth 5. And that's how you pick your scale. So it's worth 5. Now, let's say if you get like 5.5, then you have to round up to 10. Or if you get 6.8, again, rounding up to 10. So you need to round up your numbers. If I actually chose this as 4.5 here, or sorry, not 4.5, 45, this would be 4.5. I would also have to round that up to 10. So round up to an easy number that you can graph. So in this case, 5 works very nice. So therefore, I can start here at negative 25 and go up by 5s. Notice I have to start at negative 25 because I need to include the negative 20.9 in my graph. Negative 20, negative 15, negative 10, negative 5, 0. So that's my 0 line right here. Let's continue. 5, 10, 15, 20, 25. Oh, look, it fits perfectly. All right, and so that's how you pick the perfect graph. Okay, let's also label our graph. We have time over here, and on this side here, we'll have velocity. The velocity is going to be in meters per second, and the positive side is north. Okay, how did I get meters per second? Well, I've got meters over here, seconds over there, and the positive is north according to the graph before. All right, let's graph. The first time frame or section we have is from 0 to this point. This is where section A ends. Okay, when section A ends, it ends at 1.4 and the slope here is 0. So remember, we are drawing the slopes. So this here is 0 and we're going to 1.4. And that is section A. The next section, we're going from 1.4 to 2.6. And the slope, in this case, we calculate to be approximately 21, all right? Because we're graphing. Let's say it's 21 because it's easier to graph. So you go down to about 21. So that's going to be around here-ish. And we're going to 2.6. So 1.4 to 2.6, and that's section B. The next section here, we're going for like 3 squares. If you want to remember it that way, that works too. And the speed or velocity is 0. So let's do that. Okay, so 3 squares, and it's 0. Perfect. D, last one. All right, we have the time as 3.2 going to 5.2, and then the slope is 22.5. So let's draw that. 22.5 is over here, and I'm going to 5.2, which is over there, and there is section D. And I'm done. Perfect. Okay, so we've done question 1 and question 3. Don't forget to label your axes, and there you go. Now, question number 2, I'm going to switch colors so you guys can see it better on the screen. It says find the average velocity for the entire trip. All right, we don't need this graph anymore. All right, so because to find the answer to this question number 2, you actually need this one. Now, to find the average velocity for the entire trip. Anybody remember the definition of average velocity? Well, remember, it is going to be d2 minus d1 over time. So that is technically displacement over time. That's for question number 2. Now, what's the definition of displacement? Well, I hope you remember it is the shortest distance from start to finish, and that still applies here too. The shortest distance between start and finish, or if you label it or read it, this here is point 2 and that here is point 1. So let's do it. We're going to actually calculate it. Point 2, or if you want, you can technically take the slope, which is the shortest distance between start and finish, and that's exactly the same thing. You're doing the same thing for both. So this here is average velocity. Okay, so let's actually take the point. The point here is going to be, if this is point 2, it's going to be 65 minus 45, and this here is 0 for time, and this is going to be 5.2. Perfect. So we got now 20 divided by 5.2, and that is going to give me an answer of 3.8 0.85 approximately, I'm rounding up, meters per second. You'll notice this is a positive slope, which is good. You get a positive answer, and so meters per second north. And there you go. So that's how you do question number 2. If you have any questions, feel free to contact me. Go ahead and try the other questions on this package that I've handed out. Keep in mind that in the next page or on the next page, you'll notice that you could do all these sections. The only section you can't do is F because it's a curved line, and you can't take slopes of curved lines. That will be the next lesson. Also, some people were wondering about sections B and C. Where does section B begin and where does section C end or begin? Like yes. So where is they end and begin? Anyway, the point is they have the same slope because it's the same line. I've only labeled it this way because in the future, when we do velocity back to position, you'll need to know the difference. But for now, you don't need to know the difference. Okay. Again, for the next page, only do the straight lines for now. Okay. So sections A, B, C, D. Ignore F. I'm not sure where E went, but yes, ignore F. And then also this one, only do A, B, and C. Again, ignore F. The next lesson, we will focus on curved lines. Okay, bye now.